a kind of booster shot for static outside 180. I have been teaching statics for many years, and I realize sometimes students, when you go to more advanced chapters, trusses, friction, and so on, they kind of lack the fundamental knowledge, which is goes to chapter 1 and 2, the very basic, the fundamental of vector analysis, and that is where the problems are coming from. So I intend to give this an hour and some minutes, focusing on the most basic concept in statics, and then you can build your skills on a very solid foundation. Starting with, I have here 3 points. These are per meter. Very often we come across Cartesian coordinates, x, y, z, any space, any point in a space. You can define it by 3 components, x, y, z of that. There are other coordinates. We have polar, we have cylindrical, we have spherical, and so on. But this is the most common coordinates used in statics. Point A, these are per meter, point B, and point C. And I have also a force, which I introduce in a second. That force is applied on AB, the direction from A to B. So let us start with very basic. I want to find vector AB. So I'm going to go and do a wide shot. Okay. So vector AB representation is vector AB, and I want to know ijk of that. Obviously, we have these 2 points. Then talk about AB. We go B minus A. 3 minus 2 is 1i, and minus 2 minus 3. Oh, in here it should be minus 3. That's okay. So minus 2 minus 3, it's j. And obviously, in this case here, let me just correct this. So this is 1, and it's 1 minus 1 is 0. We don't have any k. So this is in meter, assumingly. I want to find the magnitude of the length AB. So the magnitude, which is representing by this, is equal to a square of 1 plus square of 1, a square root of that, which is equal to 1.41 meter. So this is vector AB. Same way, I can calculate vector AC. I write it down here. Start with the actual vector, and then I will go and calculate its magnitude. Vector AC, so 2 minus 2 is 0, and then minus 2 minus 3 is j, and 2 minus 1 is 1k. So ironically, again, the magnitude of vector AC is same as vector AB, which is 1.41 meter. So this is the first part. With 2 points, I calculate the actual value of the length of this vector, so as this one. What if I want to calculate or determine the angle made between these 2 vectors? Call it alpha. One of the most common application of dot products is to finding the angle between 2 vectors. So let me write down here. If I have vector A dot products vector B, this is equal to the magnitude of vector A multiplied by the magnitude of vector B. This is numeric multiplication multiplied by the cosine of the angle. This is 1. And also I know that A dot products is XA XB plus YA YB plus ZA ZB. So if I want to find the cosine of that angle, the cosine of alpha, which is the angle between these two vectors, is this value, which is this. So xa, xb plus ya, yb plus za, zb divided by xa squared plus ya squared plus za, excuse me, za squared, multiply the magnitude of the second vector, which is xb squared plus yb squared plus, and simply I can calculate the value of the angle by writing down the cosine of alpha, the angle between AB and AC, is equal to, here my AB, here my AC. So you see, I of this is 0, so it's nothing. K of this is 0 is nothing. Then it's going to be 1 by 1. And the magnitude of these two are given here. So it's going to be, it is going to be conveniently equal to half. And from here, the angle is 60 degrees. That's the easiest way. So I find the angle between these two vectors, which is 60 degrees. That's one of the application of dot products. So you find the angle between two vectors. So now, the other application of dot products is you want to find a projection of a vector on a different direction. Assuming AB is along with a force F, so I just put the force F here. This is force F, which is 100 Newton. And I want to know how much of force F here, how much of force F is applied on the direction of AC. You might say, what is good for? Well, let me give you an example. If this is a pipe, and here is the direction of force of my wrench, I want to know how much, and my intention is to press this pipe toward the wall. So I want to know how much of this force is acting in this direction. Obviously, the force parallel to AC pushing it toward the wall, the force parallel to it, it doesn't create, it creates a moment but does not create a parallel force. So I want to know how much of force F is applied on AC, or what is the projection of the force F on AC. For doing that, we have a few steps. Number one, I have to find the force F, because all I know, 2 points, A and B, I know the forces along AB, and I have the magnitude of the force. Step one is I must find the unit vector of AB. So the unit vector of AB, UAB, is equal to the vector AB divided by its magnitude. And that is this vector here divided by this value. So if you do a simple, it ends up to be if you have any doubt, you will say, okay, let's calculate the length of this vector. This is squared plus this is squared, the answer would be 1. Unit vector has the magnitude of the unity, 1. So this is the vector. And then if I want to find the force F, I can multiply the magnitude of the force F, which is given here 100, simply multiply as a numeric multiplication of a number by a vector by the unit vector, which is this. And the answer is, and I think we can see it here, try to squeeze it here. Or maybe just Yeah, I think we can write it down here. So it's going to be 50 root square I plus 50 and J Newton. So this is the force. Now you want to find the projection of this force on this. Next step is you have to find the unit vector of AC. So the unit vector of AC is this divided by this, which end up to be K. And the next thing I want to do is I want to do the dot products of these two. So the projection of F on AC is equal to the dot products of force F, dot products of the unit with the unit vector of AC, and that is obviously equal to the forces here. This one is here, so you can again see that what you have here is this doesn't have an I, 0. This doesn't have a K, 0. It's this multiplied by this, which end up to be right on 50 Newton. You might ask, okay, what does it mean? It means half of my force is applied along AC. Was it a different way I could get the number? Yes. I prefer this method in 3D, but yes, there was, because you know that the dot products of two vectors is the magnitude of the first one multiplied by the magnitude of the second one multiplied by the cosine of the angle. So therefore, this term I could have written here magnitude of the force, which is 100, magnitude of the unit vector, which is 1, we already know that, multiplied by the cosine of the angle, which is cosine of 60, we calculate that, which is going to be 1/2, and the answer would be 50 Newton. Pretty much the same thing. So that is as far as the calculation for finding the projection of a force in a direction. So you might say, okay, how about the perpendicular? So in that case, if I write down here, so this was my force F, I broke it down into this, which is 60 degree, and this. So this is my F perpendicular. This is my F parallel. So that would be very simple, because I need to be correctly, I may make it a little less just to be perfect. So it's going to come like this. This is my F. So this one is equal to 50. I know that this square plus this square is equal to this square, meaning in a vector notation, F is equal to F parallel plus F perpendicular. In a linear algebra, then you do the actual values here. So it means 100 is equal to this square plus this square. So from here, obviously, you can calculate the value of the parallel. So maybe I delete the top part and then we continue. And now we continue in this formula here. Obviously from here, we can simply calculate the F perpendicular is equal to F square, actual F minus parallel, which end up to be square root of 7,586.6 Newton. Was there another way to do it? Yes, you could look at this here and you can simply say that this angle is 30 degree. Obviously in this case, if you call it X parallel is 50, which is F cosine of 60. The other one is going to be f sine 60 degree, which is 100 multiplied by 0.866, which is 86.6 Newton. That's exactly the same way. So this is as far as the dot product is concerned. So the all calculation, finding the angles, finding the projection, and breaking a vector into two components. Now I would like to go next step. I would delete this part, leave this part, and we talk about the cross products and application of cross products in linear algebra. So now let's talk about cross products and application of cross products. Cross products has quite a few applications, but one of the most important one in statics is calculating the vector of the moment that a force make about a point. So if, for example, this is my force F, and this is the point C, I want to know how much this force, which we calculated the force, makes moment about point C. So before going that, I want to introduce, I'm sure you learn in linear algebra, determinant, but just briefly I will go over it, how to calculate it, even for people who are outside of a UBC or haven't taken the linear algebra. So we know that determinant, it's quite a bit of application has in linear algebra. So but this is how to calculate that. So if you have a vector here, A, B, C, D, E, F, G, H, I, this is a square matrix. You want to find the determinant of the matrix. So the calculation is this. You have to break it down. There are different ways of calculating, but one of the easiest way for a 3 by 3. If you have 4 by 4, you break the 4 by 4 to 4 3 by 3, and each 3 by 3 to 3 2 by 2, and 2 by 2 become one action. So in a sense, for a 3 by 3, you have 3 components. For 4 by 4, you have 12 components to do the mathematical calculation. So, but for here, let's just do that. What we do is this: you cross here and cross here. So what you leave, I do like a you left with this. Determinants of the 2 by 2 matrix is this multiplied by this minus this multiplied by this. So EI minus FH. Then you multiply this by A. And the first sign is positive, negative, positive. So if I want to write down correctly, so here I write down slowly, it's A multiplied by EI minus FH minus B, no, you cross this, DI, so cross this, DIFG. So DIFG. Then plus C, cross this, DH minus EG. So this is what we have. So maybe I do one examples and then we can see how it works. So just randomly I put something here: 2 minus 2, 3, 1, 2, 0, 2, 1, 1. I want to calculate this determinant. Cross this. I write 2 here first. Cross this. This multiplied by this become 2 minus 0 is 2 by 2. That's the first term. Then I have minus 2 here. Cross this. This multiplied by this. It's 1 minus this. So it ends up to be 1. And then plus 3. Cross this. This multiplied by this. 1 multiplied by 1 become 1 minus 4 is minus 3. So the answer of this is 4 minus 2 minus 9. And obviously, the answer would be minus 7, whatever it's the unit or whatever we have here. So this will be the how to calculate a simple determinant. There are other ways too, they can write it down, underneath each other and side by side. But this is what I like here. This components multiply by cross this components multiply by this, and so on. So this is the value. So I'm going to delete this, and then I'm going to write the actual application of cross product. So now we have the force F. I copied from the previous screenshot. So this is the force. This is the force here. And I want to know how much force F create moment about point C. So in this case, the moment that the force creates, so moment, we don't need to write the sum in this case, there's only one. For the next one, we write the sum. So the moment F create about point C, this is a vector. It is the cross products of the vector distance, I call it RC vector, by force F. So what is RC, or the distance vector? Is connecting the point that we are calculating C to anywhere to the vector F, or even along with vector F. Often in a realistic case, so you have a cable and you want to know this cable, there's a force, you're under tension. You want to know how much this force creates a moment about the other side. Obviously, the most convenient is either you find the beginning or the end of the force. So in this case, obviously, for us is easy because we have the beginning of the force right this point, A. So therefore, in this case, the vector of distance is the vector CA, not AC. Previously was AC, not CA. And this is equal to CA vector cross products of F. So this is equivalent to I, J, K, X component of distance, Y component of distance, Z component of the distance, and here we have X component of this force, Y component of the force, and Z component of the force. So the moment that the force F creates about point C, IJK, distance vector, which I repeat again, connect the point to anywhere on the force, including beginning and end, or even along the action of the force. So you could have simply here extended this, and I calculated this distance. But of course, it is not needed here in this case. So let's just plug these values here. I, J, K. So the distance CA, we have AC. The CA is obviously the opposite. So it's going to be 0, minus 1, minus 1. If you want to do it another time, so CA is A minus C. 0, this minus this become minus 1, and 1 minus 2 become minus 1. And the force, we have it here, 50. This is the I, and here is the J, and here is the K. So let's just write these things down here. I write I here. Cross this, cross this. This multiplied by this is 0, minus, minus this multiplied by this. So in that case, it would be plus, because minus minus would be 50.2. So this is the I component. The J is negative, I write here J, and then I swap it the other way. Cross this, 0, minus, and then you have another minus, become -1 multiplied by 50 square root of 2 minus of that, and then the sign here is also minus. So they end up to be minus 52, and for the k, cross this, this multiplied by this is 0 minus this multiplied by this, which become the positive. So become 50, like here k, 50, and here obviously is Newton meter. So you just modify that, and the answer would be 50 I minus 50 J plus K Newton meter. This is the force created by, the moment created by the force F at the point C. How do you calculate this magnitude? It's very easy. Square plus a square plus a square root of that, which I believe is going to be, let me do the math here. So it's going to be 22 point, so it's just simply right here, 50 square root 2, square of that, multiply by 3, and the square root of that, the answer is 122. Maybe I write down. I write down here maybe. So the magnitude of the moment F about C is 122.47 Newton meter. This is what I suggest you to do always, to calculate the moment of a force created about the point. So easiest way. You could also break these to 3 components and do for 1, which I don't suggest that. It could a little bit get confusing. This is the method you should do. So now I go and erase the entire light board, and then I have a brand new question. So, and then we wrap up. So you can just make a note of these. So here is a brand new question. The question is, here is a truss, and I have 1, 2, 3, 4 forces. You may not see the force number 4, but that's okay. I will show you later. So you want to find the moment that these 4 forces create about this point. We call it A. So the objective is find the sum of the moments about point A. First thing you see, well, you have the dimensions and the size, except for this force, F3, the problem is not given either the angle nor the magnitude of the force. So you say, how can I do that? So, I mean, there are so many variables. So this is in a first glance, but when you look carefully, you realize that this force, because it's passing through the point A, the moment that force 3 creates about point A is 0, regardless of the angle and the magnitude. Another way to explain it is the moment is 0 because the distance is 0. So we have only 3 forces that they create moment. With the same token, if I break these forces into components, in this force F1, so this is the Y and this is the X. The X component is passing through the A, it does not create a moment. So X of this and X of this, they do not create a moment, only the Y of them create moments about point A. When it comes to this one, it's the opposite. The Y is passing through point A, only the X create moments. That's observation 1. The next thing is you have to realize the direction. So conventionally, anything is counterclockwise, we call it positive, clockwise, we call it negative. I tell my students, I don't mind, you do it the other way, as long as for the moment you have this arrow direction, is it clockwise or counterclockwise on the top of the moment, and when you do the summation, add them, you make sure that they are the correct sign, positive and negative. So let us start with this force. So obviously the x component of this force, it's this one is 0. The y components makes a moment. I simply write it down here. It looks like as if like this. You have one force here. This is F1y. And here is a distance, whatever is distance, we call it x. And here is the point. You know, if you ever get confused, how does it work? You put your elbow in this point, and you put your hand here. If I press my hand down, what is the direction of motion? The hand moves like this. So this is obviously counterclockwise. Same thing for this force. So this force, the y component is here. This is creating a counterclockwise as well. Let's talk about this. Is no need to talk about that. Is obviously 0 for this one. So it looks like this representation. It looks like this. So here is point A, and this force x goes here. Is F4x. Now it doesn't matter. After my elbow, you can put something like this guy here, like this. So if I move this one here, how does it work? This is still moving counterclockwise. So this is also counterclockwise. So all of these forces about this point create a counterclockwise. So they all have the same sign. But let's just do the calculation here. So I do it in one shot. If you don't feel comfortable, you can do it in separate. I write sum of the moment about point A is Fx. And if you want to write the distance first to be kind of in agreement with the formula, is distance multiplied by the force by the sine of the angle. Obviously, sine is 90 degrees 1. So the x component of this is, if this is 30 degrees, the y is cosine 30, the x is sine 30. Or you can say that this angle is 60, is a cosine 60. So the distance is 5 meters multiplied by f, which is 100. I write it like this, maybe it's better. Multiplied by, just 100 cosine of, again, this angle is 30, so cosine 60 or sine 30, either way. So write it sine 30. So this one is counterclockwise, the positive one. So as this one here, so in this case, it's actually F2. The distance is 3. Just delete this. So F2 is 200. And in this case is cosine of, maybe I hit this guy, cosine of 30 degrees. So this is again the same direction. And this one, so sometimes you get something like this, you know, it's pretty simple. It means that x component of this is 4 divided by 5.8 and y component is 3 divided by 5.6. So 0.8 of 300, which is 240. So it's plus distance of 7 multiplied by 300. 4 divided by 5, and this is also counterclockwise. So let's just do the values here. So it's going to be 5 multiplied by 100 multiplied by sine 30. I have to make sure I am in degree. So this is 250. I do one more time. 5 multiplied by 100. The answer is correct because this sine 30 is half. So this is equal to 250. I keep doing this. Plus, in this case here, is 600 multiplied by cosine 30, which is 0.866. So it's 519.6 this way, and plus 7 multiplied by 240. It's 1680, and the answer is, in total, is 2,449.6 Newton meter after clock. This is the simple calculation of the moment. So now you might say, what if we want to calculate it at, I'm just making it a little more complex. So let me just move this point, and instead of this point, I want to do about this point. This is my new A. So much more different. In this case, if there's something come up from there, so both x and y of this create a moments in this. So as xy of this, so as xy of this, so as xy of this. So in that case, you have 1, 2, 3, 4, 8 total components. In the previous question, I'm just going to bring it back here. You could have also calculated these two by simply, as we did here, do this force multiplied by distance multiplied by the angle, or this force multiplied by this distance multiplied by the force by the sine of the angle. You would have got the same result. So this, what we went through, is it's a very basic. Maybe you say that, oh, it's so basic, but these basic are required for you to move forward and do more in-depth analysis. I certainly hope you benefit from this kind of brush up lecture on static. Thank you.